thanks to the Accelerator for having me today. I'm really excited to be here with you all. And I'm going to take a moment to share my screen so that we can kick it off. Hopefully you have it. So as Kevin said, I'm a passive house consultant and teacher, more the former than the latter lately. And tonight I want to talk to you about window performance modeling. And I think a reasonable, an alternate title would have been, why is my passive house consultant being so difficult? Because that is the position we find ourselves in quite often when we're consulting on windows for passive house. People ask a simple question: can I use these windows in my passive house? And we give the tried and true passive house consultant answer: depends. It depends on what kind of dryer you're using. Depends on what kind of hot water heater you're using. All these absurd things. Why do we do that? Well, let's dive into that and understand exactly what goes into deciding or to specifying windows for passive house projects. All the information we have to have at our fingertips in order to analyze the products that we're using and to determine whether or not we can use them at our projects and if they're meeting the certification criteria that are set out for us. So can I use these windows in the project? Well, let me take a look at just a couple of things. I need to know the U value of the frame, if there's condensation risk associated with the frame. So I need to see some testing for that. Is the frame airtight? Do you have the ISO testing for that frame? Also the glass. It's not just the frame, it's the frame and the glass. I need to know about the glass. I need the U value of the glass, the G value of the glass. What's the G value of the glass? It's the same thing as the solar heat gain coefficient of the glass, except it's not exactly, it's kind of different. So we need to describe to people what that actually means. There's a spacer. What's a spacer? The spacer holds the glass apart. Why is that important? It's part of the performance of the window, and so we have to include that as well. Does the glass, the frame put together, actually deliver thermal comfort passively to the occupants of the space? We don't know. We have to evaluate that. We do that using ISO testing. Then we need to also look at the installation details. It's not just the window itself, it's how the window goes into the building. You can have a passive house building and a really high performance window and put them together in such a way that neither one of those things really works very well. So we have to be really careful that we're getting all the performance that we expect out of our walls and our windows, and that comes down to the detailed level. And when that window is installed into the wall, into the assembly, do we have condensation risk? We started off with a window that had very low condensation risk. We looked at the performance characteristics of that window before we put it into our detail. Did our detail mess that up? Well, we have to look at it and see. So there's all these things that we have to evaluate in order to even know if the window is okay for the project. And the poor homeowner is just like, I don't know, I just found these windows online. Please tell me that I can use them. It's not that simple, unfortunately. It depends. So let's look at the frame performance first. Many of us in the United States and maybe in North America in general are familiar with NFRC ratings. So that's the National Fenestration Ratings Council. And you can see here, this is sort of a typical certificate that you get from the NFRC. It provides the window U value, the solar heat gain coefficient, the visible transmittance of the glass, and sometimes even the air leakage, and a condensation resistance number. And you might think, fabulous, I've got the information I need. I can plug this into my energy model and find out if these windows are going to work for my project. However, these are not the data that we need. This is a whole window U value, a whole window solar heat gain coefficient number, and they're just not detailed enough for what we're doing here. The values that you see on this page are based on a typical window size. So for a casement window like the one here, that's 600 millimeters by 1500 millimeters, or 2 feet by 5 feet tall. And every window made by this manufacturer, regardless of size, has this same U value and same solar heat gain coefficient associated with it, according to this modeling protocol. We know that's not true. We know that a larger window will perform differently than a small window because the frame and the glass have different performance characteristics. And the solar heat gain coefficient is going to be different for a larger window and a smaller window because we have more frame, less glass, etc. So this is necessary and sufficient for code compliance. It's neither one for passive house compliance. And so we need to have different data from our window manufacturers that help us build our energy models and help us understand whether or not we're meeting the passive house standard. So we need the U value of the frame, so specifically just the frame, not the glass, nothing else, just the frame. And so the U value of the frame is quantifies how much heat flows through the frame. So a lower number is better. And how do we do that? Well, hopefully the window manufacturer has done a bunch of testing and they can provide that information to us. But if they haven't, then we might have to do that ourselves. Another data point that we need is the condensation resistance, or the what's known as the temperature factor of that frame. And that temperature factor, that FRSI that you see on the bottom right here, the arrow pointing towards it, in this case it's 0.664, that's a relationship, a ratio of the surface temperature on the interior of the frame minus the outside temperature over the inside temperature of the room over the outside temperature. So it's describing how warm that surface temperature, or that surface, the coldest spot on that frame is in a unitless way. So this is 66% of the delta T is represented at that interior surface. What that allows us to do is to take these windows and we can put them in all kinds of different climate zones, and we can assess whether or not they're suitable in terms of their moisture risk. And both PHI and Phius have certain thresholds, depending on the climate zone, depending on the building typology, depending on a bunch of different things for these FRSI factors. And we need to demonstrate that our windows, our window and door products meet these certification thresholds. Super important. If we don't meet these thresholds, then we can be sure that we'll have condensation and we could have mold and moisture risk, mold and moisture damage. And that's the last thing we want. Passive house is a standard that is designed to deliver robust buildings with very low risk of moisture damage and moisture related issues. And so we want to make sure that we're paying attention to this and getting this information from our window manufacturers, if at all possible. What does this look like? How do we actually get this information? Somebody is going to do thermal modeling of those window profiles, and we get a bunch of different values. You can see here we have 3 separate models, and these are done using 2D heat flow analysis software, and there's a bunch of different kinds. The one that a lot of people know is Therm, which is developed by Lawrence Berkeley National Lab, and it's available free. Anybody can go download it and start using it. It's very difficult to start using, but once you get the hang of it, it's okay. This is a different software that we're using here. It's a little bit more user-friendly, but it does the same thing. And it calculates the heat flow through the very specific geometry of the windows that we're using. So in this case, we have an aluminum clad wood window, and we're calculating first the U value of the frame. Next, we're calculating the Psi-Value of the spacer. So that's the additional heat loss that's associated with the intersection of the glass and the frame. So at that intersection, you have a bunch of interesting things going on. There's some sealant, there's the spacer that's holding the glass panes apart, and then some other little bits and bobs that impact the performance of the frame. And so the better we do there, the higher performing our total window will be. So we need to know what that specific value is. And then the final model we have on the right-hand side is the FRSI calculation. That's that temperature factor calculation to show that we have really good high surface temperatures on the interior surface of the window frame. And we can use that to demonstrate compliance with the passive house standard. So ideally, this comes from manufacturer. Oftentimes, you can see our logos in the top left here. We have to do this modeling because we don't get the information from the manufacturer, or we don't get it quickly enough to make the decisions in the time that we need to make them. These decisions happen in early, design development, and we need to buy these windows, particularly right now. We had to order the windows now if we want to put them in before the snow falls. And so we have to be able to evaluate these things. And if we can't get the information from the manufacturer, we have to get the information somehow. So we end up modeling ourselves quite often. So this is what the process looks like. We bring CAD in. We convert that CAD into something that looks like a section cut of the window frame. So we assign the material properties to each of the elements in the frame. And again, this information should come from the manufacturer. We'll know that there's an aluminum component to this frame. There's a thermal break material, and we'll have the thermal properties of that thermal break material, et cetera, et cetera. We'll assign all the properties and then push go, and the software does the calculation for us. It's just that easy. It's not just that easy. In addition to all these sort of modeled results, we also need to know, is this frame going to be airtight? Is this going to be good enough to help that will pass our blower door test when it comes time to test the building? And sometimes we get this information from manufacturers. This isn't something we can model well using a computer. It's something that we have to either get from the manufacturer or have some experience with. You can see here in the infrared thermography on the right hand side there. This is a really beautiful passive house lifted slide door that isn't performing very well, that isn't very airtight. It's kind of a hard thing to do, to have a window that's lifts up, slides over, and then locks into place and seals into all the right places, up, down, and to the side. And you can tell from the thermal image on the right that we're getting air leakage coming into that intersection between the two panes of the lifted slide door. So airtightness is another thing that we need to be careful of. It's not something that we can model very well, unfortunately. Okay, so that was just the frame. Now we have to also look at the glass. So for the glass, we're going to look at the U value of the glass. And again, that's the how much heat flows through the glass based on its physical properties, the type of coatings that are on the glass, the gas fill between the panes of glass. And these data sheets come from the glass manufacturer. They should be pretty easy to come by once you've decided what kind of glass package you want to use. The G value here is listed in metric units, 0.525. If this was in IP, it would be something like 0.09 BTUs per hour square foot to be Fahrenheit. But anyway, we need this information. We need to get this from the manufacturers. We also need to get the solar heat gain coefficient numbers, or the G value, G factor. Those are all the same thing. But remember, when we're talking about these sort of separate values, this is a glass only number. This is the center of glass, if you will, G value, or solar heat gain coefficient value for the glass. Whereas in many other testing standards like the NFRC, it's a whole window at solar heat gain coefficient value. So they're different. We can't really compare them. We need this very specific data. And that's what we need. That's what we need to plug into our models. We need the information about the spacers. This is, again, associated with the glass package, how we put those glass panes together, what are the gases that we use in between, and how are we holding the glass apart. We need the thermal performance of the spacer and how that impacts the interior surface temperatures. Once we have that much information, once we know the U value of the frame, the Psi-Value of the spacer, the U value of the glass, we can begin to evaluate whether or not these windows will meet the comfort criteria for passive house. And many of you probably already know about this phenomena that if we use low performing glass elements in our building, we run the risk of having low surface temperatures, which are very uncomfortable to our occupants. If we have a low temperature at the glass, and there's a good amount of it, it'll feel like we're losing heat to that glass, and it'll feel uncomfortable. Our bodies don't know how to manage that kind of thermal asymmetry and those low surface temperatures. If we're doing our jobs as passive house designers, we're trying to do all of this, manage occupant comfort passively in as much as we can. And so we want to provide a window that ensures thermal comfort without installing heat next to the windows like we've done historically. And we don't want to put a radiator underneath that window. We don't want to put heat mat around the window. We want to just have the window perform in such a way that it ensures thermal comfort without those active measures. We want to do this passively. We can evaluate the performance of the window against the comfort criteria for passive house windows and know whether or not we've made that. And that's going to be a climate zone specific thing. So it'll be determined based on your outside temperature and whether or not we provide warm enough surface temperatures with the glass. And then one of the last things we need, because windows are so complicated, they're sort of where everything important comes together in the passive house building. It's where airtightness, waterproofing, views, heat loss, heat gains, everything comes together in the windows. All the control layers have to be bound together in the windows. Because we're looking at the energy balance of the building, because we're looking at the relationship of heat losses to heat gains of the entire building, we have to know how our windows are contributing both to heat loss, so the U value of the entire window, and also to heat gains. So how solar gains are harvested or impact the performance of the building. And so we need to know this shading condition of the building. So its context, as you see here, this building is in an urban context, and so the adjacent buildings are providing some shading, but we're also recommending some additional shading because in this case we have a densely occupied multifamily building that is internally gains dominated, and we don't want all those extra solar gains as we might in a different typology. And so we're suggesting some shading that will actually bring down our cooling and also bring down our heat, bring up our heating. So we'll have to, it's a balance. We have to give a little bit of heating away in order to bring the cooling down. But that's the game. That's what we're doing when we're designing passive houses. That's how we're weighing in as consultants in these early design meetings with our passive house teams. Okay, so that's just all the product stuff. So ideally, that all came, or most of that came from the manufacturer, from the architect. It almost never happens. And so a significant amount of our work is involved in producing some of that material. But really, this is kind of where our work should begin. We're evaluating the installation performance of our passive house details. And we're going to look at the way that these windows and doors are installed into our passive house assemblies. And we're going to try to design them to optimize them such that we get as much value and as much performance out of our windows and doors as we possibly can. Because frankly, we're paying a lot of money for these things, right? These are high performance products. And we want to make sure that we're getting every bit of benefit we can from them. So we have to do this, we'll do what's known as a Psi-Value, Psi install calculation to determine how much additional heat loss is associated with the window as it comes into contact with our assembly. And what that looks like is something like this. So our energy model is not very smart. It's very useful, but it's not very smart. It deals with areas and U values. So areas times heat loss. It doesn't know anything about how that window is installed into that wall. And so we have to give it that information. And that's what we do with our Psi install calculation. We're saying, okay, you think it's this thing on the left, a perfect wall and a perfect window. We actually built this thing on the right, which is a window installed into that wall. And there's a whole bunch of things going on there that are a little bit different than what was represented in the original thing. And what's the difference? And the difference is the Psi install. So the difference in thermal performance is the Psi install, and that's what we're going to use to plug into our energy model. We're going to try to optimize these installation details so that they perform as well as they can. Oftentimes, early on in a project, we'll be working back and forth with the team, and they'll say, "Okay, let's see. Tell us how much insulation you need around the window when we install it into this masonry walls we have here." And these are tricky. In masonry retrofits, it's really hard to get good Psi installation values because you can see the window is out of plane with the insulation layer. I mean, ideally, those things would be just right together, but we can't do that because the window needs to sit where the window needs to sit, sort of out towards the edge of the building, and the insulation layer is on the inside where we have an opportunity to install it. And so we have to sort of bridge those two elements. We have to connect that interior insulation to that window, that window that's sort of out of plane with it. And we do that by insulating sort of up to and around the frame. But we need a significant amount of insulation there in order to, not have a really, a bad thermal bridge there. And the question is always how much? And really the question is how little? because nobody wants to give up any space, and we want our windows to be as big as possible. We don't want to have the windows shrunk in the opening or things like that. So depending on the situation, in this case, we had the architect asking, what if we have 1.5 inches? And 1.5 inches worked fine. We just installed some insulation in the space between the masonry and the window frame, and that gave us a pretty good Psi install, one that met our criteria for the project. No big deal. They said, oh yeah, actually, I said 1.5 inches. I didn't mean 1.5 inches. I meant less than 1.5 inches. And in order to get the same performance, now we have to do something different. We can't just shrink the insulation and expect it to perform the same way. In this case, we actually had to chamfer the brick, and you could see the difference in the brick, that dark red poché in the two diagrams. We're really asking the contractor to cut back the brick so that we can get the insulation to intersect with the window frame there. We get the exact same performance, but somebody who's not me had to just work harder. For me, it's easy. I just draw a triangle and say make that insulation, and it's a piece of cake. But for the person on site, that's a real pain. So these are the things that the architect gets to evaluate. Do I want to ask the person to chamfer the brick, or can I live with 1.5 inches of space between the window frame and the masonry? And we go ahead. Again, as with the window frames, we're going to also evaluate the temperature factors of our installation details. Meaning, we started off with a really high performing wall, and we started off in this case with a high performing door that met this criteria that we needed to for certification. Did we mess that up? Are we going to end up with lower surface temperatures than we need for certification? We need to prove that our installation details are still good and provide warm surface temperatures so that we have very low incidence of moisture or potential for mold and moisture damage. Okay, so the homeowner asked us a simple question. Can I use these windows in my passive house? And sometime later, we can say, why, yes, you can. But it's not a straight path, and it takes time. And I hope that there's people from the window industry on the call who can absorb this and understand that what we really need is comprehensive data sets from our window manufacturers, so that we can skip the whole first 3/4 of the things that I was talking about and just have a table that has all these things listed out. Somebody's done the modeling, somebody has the performance data that we can just take and run with. Because otherwise it takes us just a tremendous amount of time. Or it takes the manufacturer a tremendous amount of time to sort of behind the ball, make up the time and get somebody to do this modeling, get somebody, a lab to do the performance testing.